Yeah, okay, I'm going to record. So tonight we are going to start with the talk by Sam Witteveen. Sam is from AI Dragon from Singapore, and then he's also Google developer expert in machine learning. But I'll let Sam to introduce himself more. So time is yours, Sam.
Thank you. Okay, I'm just trying to set this up so I can see people a bit and I can see the chat. If people want to ask questions at any time, feel free. Okay, so hopefully people can hear me, etc. All right, so good evening, everyone. Sounds like there's a bit of issues with Zoom, but okay, let's get started. So a bit about myself. I'm originally from Australia, originally from Melbourne. I haven't lived there for a long time, for about 25 years plus. But I grew up quite a bit in Melbourne. Like Eunice was just saying, I'm a Google developer expert for machine learning. I was one of the first 12 Google developer experts for machine learning and deep learning appointed in the world. And that's about 5 years ago now. I work specifically with deep learning and mostly around things to do with language and dialogue systems and also generative models. Obviously tonight I'm talking a lot about generative models. I'll talk a little bit about that. I also happen to organize the machine learning meetup in Singapore. My background is in startups. I've built multiple startups. I've built 2 B2C startups with more than 1 million users. I've done a number of different things in that sort of area. For the past couple of years, I've been a mentor in Google for Startups for North America and for Asia. And the current startup that I've been working on for the past few years is a startup called Red Dragon AI. So Red Dragon does a bunch of things. Let me just show you some things about us. So we were founded in 2017. We're a Google partner. We do a bunch of things that relate to sort of consulting and prototyping stuff for Google customers and for other people. We also do a lot of research. So we're in a lucky position where Google has sponsored some of our research. We've had papers at NeurIPS, at EMNLP, at NACL, at quite a number of different conferences. And one of the things that we're sort of heavily focused on at the moment is very sort of the idea of advanced conversational AI and what we call digital personas. So this is using sort of generative models to create digital humans that people can then interact with. Eunice, do you want to let people in as they come in?
Yeah, sure. I'll take care of that. Yeah, don't worry.
All right, so tonight I'm going to be talking about generative models, and I'll tell you a little bit about how this sort of talk came about. So I can't actually see the participants, so we don't have like a hands up or anything like that. But there's a conference, I'm sure some of you know about, the conference called NeurIPS, which is run in sort of December each year. For the past couple of years, it's been online due to COVID, but this is sort of like the premier AI or really machine learning related conference in the world. And for the past couple of years, one of the things that we attend this conference, we've had papers at the conference, and I always like to pick, at the end of each sort of conference like this, I pick a talk that I will give, which sort of sums up some of the new things that people are talking about and some of the general directions of things, where things are going with machine learning and deep learning in this conference. And so last NeurIPS was in December 21, just a couple of months ago now. And one of the key things that became obvious to me was that there's definitely a lot happening in the space of generative modeling here. So, okay, I see someone saying that we host the NeurIPS remote locally. Okay, great, fantastic. So I'm wrapped that you guys know what it is, right? Okay, so I'm going to talk about, not just papers from NeurIPS, but also some things that have been since NeurIPS, and also just some of the sort of general field of this, idea of generative modeling. Yeah. So this sort of brings about the first question, which is, what is generative modeling? So I would say, the definition I'm going to sort of give, or the things I'm going to talk about tonight, is we're generally talking about a deep neural network. And we're talking about something that's trained to generate some form of output. This could be an image, it could be sound, it could be, a variety of different things. It's quite a different model than, say, a classification model or a regression model here. We're definitely, doing quite a large output, usually in some way. And the goal with this is normally that we're trying to learn a distribution of underlying data so that we can then generate samples from that data distribution in a way that would be something that maybe is completely new, but could have come from that data distribution. So the classic example that you'll see, that I'll show a few examples of tonight, would be faces, right? A lot of people have done the, this person does not exist sort of thing. And in that case, you're basically training on a data set of a few 100,000 faces, and then you're trying to generate new faces that are not in the data set but could have been in the data set. So this is definitely a challenging sort of task, because we've got a whole bunch of things in that data that is, that makes it very difficult to model. And we also then need to model it in a way that we're sampling one example from that. So we don't want, for example, just to be able to sample things that are the mean of it, or, that kind of thing. The last thing that I would say that has become sort of standard in generative modeling is that we often want to condition the output so that we can guide this generation. So rather than just, have it generate, if we're talking about, say, MNIST, MNIST digits, rather than just generating any MNIST digit, we want to be able to tell it, right, we want you to generate just number sevens, and guide it in some way, for that kind of thing. So this is sort of, what we're talking about tonight. All right, so types of generative modeling. There are a lot of different types of generative modeling. These range, a variety of different techniques, from things, that started 10 years ago to things that are literally only, a year or two old. For some of this stuff. Tonight, I'm going to focus on 4 main areas of generative modeling. I'm going to look at GANs, or generative adversarial networks, which I'm guessing quite a few of you already know about already. I'm going to talk a little bit about variational autoencoders, which is an idea that was popular going back sort of 8-9 years ago, and has sort of come back in a different form now. I'm going to talk about diffusion models, which is a much newer version of generative modeling. And I'm also going to talk about neural radiance fields. So I'm going to leave out some of the other stuff, like autoregressive models would be things like, your GPT language models and stuff like that, where you're predicting something in sequence. I'm not going to talk about normalizing flows or score matching models. These are also really interesting things. Just for time's sake, I'm going to sort of focus in on these 4 areas. I'm going to start off, though, by talking about some general trends that we're sort of seeing. So in the past, you would have generated, you would have seen papers like this, where people were, generating MNIST, and I presume everyone knows MNIST. By the way, if anyone wants to ask a question, feel free to ask questions. I can see the chat as we're going along. But in the past, people would have generated things like MNIST. They would have generated very low resolution faces, these kind of ideas. And this was state of the art, less than 10 years ago. So I just want to sort of set the bar of where we've been and where we've sort of come from. If we're looking at GANs specifically, we sort of saw that in 2014, at best, we could do something in black and white. By sort of 2016, 2017, we could then do color faces. By 2017, we actually then started to see sort of the precursors to the style GANs, which was the progressively growing GAN, this one on the right here, which actually started to bring about photorealistic generation here. And it was still very limited in what you could do, it's still flawed in many ways, but we actually then started to get into, and this is literally only 5 years or less than 5 years ago. So some general trends that we're seeing is that definitely quality is getting better and better. But beyond this now that sort of the photorealistic thing has been achieved, people are much more interested in, okay, where do we go for the next step for this? And part of that is going to be things like multimodal models. And part of that is going to be a lot to do with guided generation. So I'll talk about, some of the techniques that people are using for these things. So multimodal is one that's very hot at the moment. So here are sort of 3 models that focus in on multimodal stuff. We have the newer model, which I'll talk about later on in the talk, from Microsoft Research Asia, which just came out very recently. We have DALL-E and Clip from OpenAI. So you can see here we're generating, things that all these models are starting to use not just images as a modality, but often text and other things as a modality. At Google, Google's basically got the MUM model, or the multi-unified multitask models. These are not generative per se, but they're being used for a lot of different things, like search and stuff like that, where people are looking at doing things that are multimodal and not just purely text-based or something like that. Another key thing is the guided idea, the guided generation. So when we look at the guided generation, we're definitely seeing huge changes in the past year or two for this. So there are sort of 4 main ways that you can do guided generation. The first one relates to sort of latent codes, or and I'll look at this when we sort of look at some of these things in depth as we go through. This is basically where you've got a continuous vector that you're using some noise or something like that to feed into a generator, have the generator then be able to do stuff. This can be guided in many ways, and I'll talk about that. Beyond that now, we're starting to see things like text prompts. So the lower left image here is from DALL-E, and this is basically using a text prompt where you can actually guide the generation with saying something like an armchair in the shape of an avocado, and it is actually able to produce things like this, even though these were not real images from the training set, etc. Now, these are probably very cherry-picked from the overall thing, but it's still pretty amazing that it can do this. Some other ways we're seeing that people are guiding generation would be things like masking and sketching. So the top right here of where this picture originally had a person walking along holding a surfboard. If we just sort of mask them out and then regenerate, we can basically just take them out of a scene. This has become a very popular technique to use. And then another one that we sort of see is where you see image prompts used. So here we can see that this is sort of like a GPT style model, where you're basically saying, okay, I'm going to feed it in an image as a prompt, but I'm also going to give it some text here, and I'm telling it that I want the exact same image as I'm feeding in, but I want you to sketch it. And you can see that the model is able then to basically sketch out, different examples. So this is what we refer to as sort of guided generation. Another thing I'm going to sort of set up is, is just some evaluating criteria for evaluating these things. So the things I would say that you want to keep looking out for in generative models is, okay, how is the generation done? How efficient is the generation? And how can the generation be guided? So you'll see that there are many techniques for how these things are done, and there are techniques that end up popping up in multiple scenarios over multiple years as well. So the first one I'm going to talk about is GANs. I'm guessing that most people have a reasonable idea of what GANs are. If you don't, just very briefly, again, is where we sort of set up two networks. We have a discriminated network and a generated network, and we have this adversarial relationship of where these are basically fighting against each other. The generator makes some data. We then present some real data and generated data to the discriminator. It has to be able to tell the difference between these. And you want this sort of balance with these things. The goal with this kind of thing is not necessarily to bring a loss to zero like in a normal sort of model. We want this sort of balance of where sometimes the discriminator wins, sometimes the generator wins, but overall they're both getting stronger. And this can be really difficult to sort of do. And it took a long time for people to work out ways to do this. One of the sort of best examples of this has been the style GANs. So these came out of NVIDIA, really starting with the precursor to the style GANs in 2017, the one I talked about before, the progressively growing GAN. But the original style GAN came out in 2018. And this was, probably the first model that could just generate totally large amounts of images of human faces, and people really couldn't tell the difference between these. It's not like it was perfect. There were some issues with this. So this was sort of the first one to accurately create very high resolution images. It was a sequel to the progressively growing GAN. It uses a very high resolution data set called the Flickr Faces data set. It also works in other domains, so it's not just faces. One of the ones that I like a lot here is the idea of these bedroom scenes. And if we look at the bedroom scenes, this is where we sort of see the strengths of a GAN here, in that this is not taking some sort of mean or anything in here. This is basically what it's doing is it's looking at it and generating something that it thinks would be there or not there. So you'll see, for example, that like the curtains, there's never really half curtains. There is either curtains, either there or they're not there. And the same is pretty true with the paintings on the wall too. So we don't get these sort of blurred halfway sort of things. And this is one of the sort of things that set, the early style GAN, let me just meet someone, set them apart from sort of what was going on out there. The style GANs, though, still had, quite some major issues for the first one. And you would see these, what they were called droplet artifacts. So these are basically where what was happening is as the model was sort of upsizing the image, it would not do a good job at certain parts. And you would then see these artifacts. And if you knew what you were looking for, it's actually quite easy to tell the, a style GAN, original style GAN image from the real thing, pretty easily. And certainly if you're trying to train a classifier, it can learn, quite quickly how to do that. So after that, they brought along style GAN 2. So this did away with a few different things. One of the key things, though, was it introduced a new type of normalization, and it introduced a really good way of handling the latent space a lot better. Now, I'm not going to go into this tonight. We don't really have time. But what it did, rather than just working in what we call Z latent space, it translates it to a more even latent space. And that allows for better interpolation, which means when we're taking that latent vector and interpolating between latent vectors, we can actually get much better images out from this. And this is sort of, style GAN 2 was the first one to really sort of move into this. And this became, this became sort of like a real trend that we sort of saw from this. So after this, we had style GAN 80A, which was an adaptation to this. So style GAN 2 is roughly 2019. Style GAN 2 80A is 2020. And then style GAN 3 was 2021. And this was at NRIPS last year. And one of the things that this introduced, so this allowed it to sort of fix up a lot of the problems that were still in style GAN 2. And one of those is that the GANs tended to be really good at sampling something, but if you move the latent space a little bit to try and move the image a little bit, you would see flaws in this. So, and the reason for those flaws was basically that they weren't, StyleGAN 2, etc., wasn't equivariant to translation and rotation. So that's what StyleGAN 3 introduces to this. So it basically means, let me sort of show you what it means in a picture rather than looking at something text. What it means that if you look at this guy on the left here, you'll see that his beard doesn't really move. The text, this is what we call texture sticking, and it's just sort of sitting there. Let me just play that again. Whereas, and it's just sitting, even though his face is moving behind it. Where the guy on the right, the beard is moving, perfectly with the face. So this is what happened in StyleGAN 2. And then StyleGAN 3, fixed this up. So this is one of the key things from the GANs. And it's not just, this is a nice sort of way of seeing it. It turns out that this makes much better interpolations as you're going through this stuff too. So that you could go from one image to, translating through to other images in a much smoother context too, without weird artifacts. So StyleGAN 3 was definitely one of the interesting papers at NeurIPS this past year. And one of the things that I love about the NeurIPS conference, and if you get a chance to sort of attend one online something, it's definitely worth doing that, is that they have poster sessions. And in the past, when you would go along to the physical conferences, it really can be quite hectic in that you've got 90 minutes to go around and look at maybe 100 different posters, and the popular posters will have like 20, 30, 40 people around them asking questions or looking at different things. The interesting thing is when they move this online, they made a virtual sort of version of the poster thing, and they just left them open for a few hours. And then the authors would just sort of sit there and take questions. And one of the great things with this is that you could go in and actually talk to these people. For me, I'm very interested in GANs. I went along to the StyleGAN 3 things, talked to the authors for quite a while about not only StyleGAN 3, but more the directions of where this whole thing was headed. And that's sort of what led me to this talk, actually, was that the interesting thing was that they were not as hot on some of the GAN stuff going forward, but they're now starting to look at, other things internally at NVIDIA, and one of the authors actually said to me that, well, in many ways, the GANs is kind of getting to be a solved problem, that we can generate, all these sorts of things. So I actually doubt we will see a StyleGAN 4. I think you'll see, new things coming from this team, but not necessarily like this. So this StyleGAN, is definitely one of the sort of key things for this. Next, another paper that was at NeurIPS, which was a GAN paper, is a cool little sort of trick, and this is called projected GAN. So if you do want to train GANs, if that's something that you're interested in, one of the things you'll know is that training up these models can take a long time. I've trained up quite a few StyleGANs, and I'll normally leave them running with multiple V100s for 5 days plus to be able to get something that's quite good for this. So this paper really interested me because this is basically looking at how can you make GANs converge faster. And they've got a really nice little trick in here. And what they do is that they basically just created a better discriminator. And the discriminator, I'm not going to go too much into the details. You can go and have a look at the paper and stuff yourself. But what the discriminator does is it looks at parts of the image, and it looks at parts of the image in sort of patches. So that in itself is not a new thing. We've had this sort of idea of patch GAN in quite a thing for a while. But what this sort of does is take another network and then passes it through that other network in these small patches, and then uses that to basically then predict, the generated versus real as well there. And you can see that they actually do it at different layers in the network as well for doing this. So they can actually do different predictions, different sort of discriminators at different layers. Now, one of the cool things about this is that this model itself actually doesn't even need to be trained. You can actually just have random weights in there. And because it's sort of looking at a modified convolutional pattern, that turns out that the random weights work fine because real images will have a certain pattern and fake images will have a different pattern. So obviously the closer the fakes get to the real, the more that pattern will sort of fit. So this is kind of interesting, and they try out, a number of different networks using VGGs and stuff like that there. All right, so that's projected GAN. If you see, there's another one. Actually, I think I might have a slide in here later on. There's a new model out from the same people. That's getting quite popular over the past week or two, called StyleGAN XL. And it's actually just StyleGAN 3 with this projected GAN trained up on ImageNet. So I think I've got a slide about it in here. All right, so GANs. One of the big things in GANs is really interesting is the guided generation. It turns out that we're going to feed in these sort of vectors, normally something, a vector that's sort of 512 long. And what we would like to do is be able to sort of work out something about that vector. So one of the ways that you can think about this, I find, so for those of you who've worked with latent spaces, you'll know this quite well. If you're new to this, just think about that. I always like to think of vectors as being, locations in an n-dimensional universe. So if we've got a three-dimensional, we've got a point in a three-dimensional space is a vector of 3. If it's in 512-dimensional space, you can think about it still in a point in space. And the interesting thing is that you can then manipulate those areas tend to produce certain things. Now, one of the interesting things is it's not like one of the flaws that a lot of people think is, well, okay, if I want to disentangle the semantic representation here, maybe this number here is going to represent, smiling or not smiling. And it turns out that it doesn't actually work like that, right? That these are not disentangled representations in the sense of along these axes that we have here. What it actually works out is in directions. So if you think about it, a 512-dimensional vector, we've got a lot of different directions that we can push in, and different directions can produce things, can make changes, things like a smile, like the gender. And we can then sort of translate through, from one point in space to another point to generate, lots of images for doing this. So the idea of projections is a really key thing in GANs. Now, some of you, I'm sure, have experimented with this quite a bit before, and some of you might find it, new. But the idea is that if we want to, find things in GANs, we've got to basically work out the projection by manipulating this latent vector. One of the best ways that we can do this is to basically take a loss against the latent vector, not against the weights of the model. So that allows us to do things like what this paper introduced, and actually this idea has been around for a while. This is just a much more efficient way of doing it, of where you basically have an image, and you then feed it, in this case through an encoder, to get a latent vector. And then you use that latent vector to project out through the StyleGAN, and you then take a loss against the images. And what this paper basically improved this, by an order of magnitude. So in the past, this would take a long time to do, to be able to find a picture of someone in a StyleGAN kind of thing. Now you can do this, very quickly. You can go through it. have a look. I've put a link to the demo there. It's quite nice that you can basically just upload an image, and you'll see that it'll find the closest match in one of these style GAN models. And really what it's doing is it's finding the latent representation, or that latent vector that represents that image. And once we've got that, we can play around with a lot of things. So if you see a lot of things of where people are, taking a picture of someone and aging them, that can be done by this sort of thing, where we basically find the latent vector for the person. We then find the direction for aging, and we just move the vector along in that direction. And that turns out to be a really useful task. Another one that's become a really cool sort of guided generation task is this idea of clip. So I can't see, unfortunately, when I do it on the webinar one, I can see people's hands if people put their hands up. But anyway, I'm sure some of you have heard of clip. So this is basically a model that came out of OpenAI about a year back now. And what this is basically all about is doing sort of, they call it, stands for contrastive language image pre-training. Really what it was that you want to match up embeddings of text and images so that you can use text to predict an image and images to predict the text for this. So they trained up on about 400 million images and text pairs from scraping the internet. And what it allows us to do is it allows us to then take a loss between an image and some text. And then we can manipulate the image by changing the text. So the text produces an embedding. We can then use that embedding to manipulate the image based on the model that we've trained it on. So this is a really nice, a really nice technique. And it came out originally from OpenAI, but very quickly, last year it made its way into the sort of style GAN world. And this is, called Style Clip. And what it allowed you to do was basically find a projection of a person and then take that projection and say, right, I want this image, but I want to manipulate it with some text. So you can see here that they're doing things like, putting an image of a person in and saying, okay, I want the hairstyle to be a mohawk, and it can take, a picture of Obama and move it. Now you've got to understand it's not doing it where it's just changing the hair, it's changing the whole vector. And so you will see some changes in other parts of the face to keep it consistent. This is kind of interesting that supposedly this cat is not a cute cat and this cat is a cute cat. So it tells us a little bit about what people think is cute, maybe big eyes, this kind of thing. I played around a lot with this when this came out. And one of the things that, we were sort of very interested in is like, okay, what could you do with people and what did it know about people? So generating things from scratch, here's images that I generated. And this is one of the things that I was really interested to try was, one, does it actually know some people? Well, it clearly seems to know Elon Musk, right? So the one on the left is an oil painting of Elon Musk. And this doesn't, exist anywhere. It's basically just, it's got an understanding, or it's got a representation. When I say understanding, I should be very careful about that, but it's got a representation of a vector of what you need to do to a vector to make it an oil painting. And then it's able to find some sort of vector that represents this thing called Elon Musk and can do that. The thing that's really funny is that then you can say things like, okay, I would like an Asian Elon Musk or an Asian young Elon Musk. And it can then basically, generate something that it believes still has parts of the Elon Musk vector, but also has parts of other conditional vectors as well. So this is sort of a fun thing to do. You can play around with this. Newer GANs. Right. One of the ones that's come out since NeurIPS, and actually we spoke, talking with the StyleGAN authors, we spoke extensively about this. The paper for this is still not out. I think it will come out in the next month or so. And this is GALGAN2. And what this does is pretty cool. So let me just turn off the thing. So this basically allows you to take an image and then manipulate this with text. So it's doing a similar kind of thing. It's not actually using clip per se, but it's using something like it. You can see that it can then basically generate things where you could take a picture and say, all right, I want this in fog, or I want this in something else. And it can do this. So it can also do the masking idea. So where we can say, right, this is a mask, like a semantic segmentation mask here. And I want you to turn this into an image of a mountain. And you can see that sure enough, it can work that out, and do that. And then it can start playing with it. All right, I want it to be cloudy, or I want it to be rainy, or I want it to be sunny, etc. So this is an interesting thing from a few points of view. One of the things that was interesting about talking to the StyleGAN authors was that actually GANs haven't made a huge headway into sort of industry. They're used for certain techniques and stuff like that, but they haven't been used a lot. The idea is that GALGAN2 will open this up a lot to different things, and allow people to use this in a much more sort of generative art way, of where you will probably see this make its way into Photoshop, is my guess, with this kind of thing. All right, so that's GALGAN2. Another one is another one that came out just recently is Stitch It in Time. So this is basically, again, using a guided generation on a StyleGAN to manipulate the video in some way where it's going to be consistent. So you can see here, unfortunately, this is not it's not in real time. It's a bit misleading how they say real videos. I'm not sure what anyway, you can see that it is pretty cool though, that you can take something like this and we can say we can do sort of the visual version of prosody, where we can actually change the emotion and stuff like that. We can change age, we can do these things. So using a 2080, these take, I think, about 30 minutes or so. It's certainly not real time for doing this yet, but it shows you, it is definitely a step, that's really interesting for this. Another one I mentioned before, so from the Projector GAN guys, they've gone and done one which is modeling ImageNet. This is kind of nice, and you can see that this sort of where we're sort of moving the dog around, this is a clear sign that this is StyleGAN 3. Anyway, but this StyleGAN XL is ideally trying to model all of ImageNet. I'll show you some models later that I think are actually better than GANs at this nowadays. But this one's interesting. It does seem to me that this paper really just seems to be more of the same sort of projecting GAN, but on a different data set. Anyway, let's move on to VAEs. So I'm guessing, for those of you who've been in the deep learning community for a while, will remember autoencoders and variational autoencoders. These were very popular. VAEs originally came out around sort of 2013, 2014. Up until the GANs sort of hit photorealism, the VAEs were still considered like, this might be one of the ways that works. And then once the GANs sort of hit their stride, people kind of put VAEs to the side. And it's only just recently that people started to come back to this. So if you don't know what a variational autoencoder is, we've basically got an encoder network on one side, a decoder network on one side, and we're basically trying to build a bottleneck. And if it was just a normal autoencoder, we would just have a single latent dimension in here. And we go for a bottleneck going down to this latent dimension and then coming up the other side. What a VAE does that's different, just briefly, is that we're basically going to make a distribution. So we're going to have a sort of a vector of means on one side and a vector of standard deviations on another side. And then we can actually do a little trick called the reparameterization trick, which allows us then to sample out of these two vectors and create something that we can then feed back into the decoder network to generate. Now, early on, this, wasn't that great. Sort of like, people kind of abandoned and walked away from these things, because what they would do is they would build images like this that were still quite blurry. There really wasn't a good way of getting the sort of crispness that the GANs had got. This was still sort of a flaw. And this was kind of up until, some DeepMind came along and introduced this idea of a vector quantized VAE. So what is this vector quantized thing? So rather than sort of bring it down to a distribution of mean and standard deviation, what the vector quantized idea does is it basically encodes it on one side into what we call a code book. And this code book kind of, you can imagine that you end up with something like a representation in the middle. And I'm oversimplifying this, but imagine you've got some sort of image and you've got these codes that sort of say, oh, well, this is a green tree and that's number 1. And, this over here, 3 is like a dog, and this 53 down here is a person or something like that. And what it does is it learns to basically make these discrete representations in the middle of the network. And then on the decoder side, it blows them back up into images. And because it's doing it from this discrete thing, it actually turns out that it works out, oh, okay, well, if I've got a tree and I've got a person and I've got a car or something, it kind of can work out how to size them and how to do it so that it looks like something from the original distribution that we were learning from. So this VAE idea really took off, originally from DeepMind in 2017. It's definitely a nice idea around sort of discrete latent space versus sort of the continuous vector idea. It was used in DeepMind for audio and speech in numerous papers. And then to be quite honest, they kind of, just left it alone. They didn't really do much with it. And until OpenAI came and picked up this idea a couple of years ago. And sort of, in 2019, 2020, OpenAI started doing this stuff with this VQ idea. So this vector quantization idea, one of the first places this appeared was in Jukebox. So this is a generative model for making music. And the idea is that you basically encode the music on one side and you get this little code books inside. Now, they actually do it at multiple frequencies and things like that. So it's not just one simple thing. But what you do is you end up with this sort of code book of where some of the codes represent artists and some of the code represents style. So and I encourage you to do a search for OpenAI Jukebox. I haven't got the link here, but you can find there's some great demos there of where you can do things like take the artist being Michael Jackson and the style being country music, and then generate something out which will generate a song that sounds like Michael Jackson singing country music. And what they do is they also feed in these, back then they were using the GPT-2 model for generating lyrics, and they would feed this in and it would, generate things out. And it is pretty amazing, the standard this could do. The fact that you could take an artist and even take their own style and generate new songs in that style, and either give it lyrics or use the sort of generative model to generate some lyrics as well. And it raises a whole bunch of issues around copyright, right? And I think this is one of the reasons why OpenAI and certainly Google haven't really sort of touched this too much, is that no one really knows. Like if I basically just learn the style of Michael Jackson, do I have to pay royalties for that? And then if I learn the style of country music in a certain artist, is that something that's copyrightable or not? So this idea is something that really really took this to the next step, the idea of VQ, vector quantization idea. Even beyond this, the same authors then came back to see to do this model called DALI. So this is about a year ago, probably about 11 months ago now, and DALI is using a image generation model, but it's using that vector quantization idea in there, and then it can also be guided using something like CLIP to actually then generate images in a certain way. So you're starting to see these things come together. for this. Sort of this idea here is this vector quantization idea is still a really interesting idea. I'll show you that the same authors now have moved on from this, though, in a more recent paper. But this idea was, very cool in its time. And then sort of taking this idea even further is a model that just came out last month, I think, from Microsoft Research Asia. This is the newer visual synthesis pre-training model. And the idea is this is doing the same thing where it's using this vector quantization idea, and they train it up on a bunch of different tasks. So they actually do, I think it's pre-training on 3 tasks, and then they fine-tune on 8 tasks. So I'm jumping around a bit, but these are the 8 tasks that are fine-tuned on. So you've got things like video next frame prediction, so that it can learn to sort of predict next frames for things. It can do image manipulation. It can do, so this is doing it in an auto-regressive, kind of way where it's filling it in here. So you can see that it can basically take half an image and fill in what it thinks the rest of the image would be. It can take a semantic segmentation map and turn that into a real image and stuff. This is definitely pretty, cool of sort of what they're doing. The other thing that I found fascinating with this paper is this example. So this, on the left here, we've got the raw video. And then here we've got different text prompt manipulations here. So we can see the diver is swimming to the surface, and sure enough, the diver goes up, right? And then with the next one, the diver is swimming to the bottom, and sure enough, the diver is going to the bottom, right? The third one is kind of even funnier. The diver is swimming to the sky. And sure enough, you can see that suddenly the whole air tank just disappears and it kind of becomes like an Ultraman or something like that. And we see that the bottom of the sea kind of turns into clouds there. So it is interesting that these models are kind of learning some representations of even some of the things that we would think of as being kind of common sense. Like if we think about, swimming to the surface, going up, swimming to the bottom, going down, the models learned, at least in this example, to be able to do some things like that. So this is definitely an interesting, perhaps artifact of this whole process that's going to be interesting to see where going forward with some of these things. So this was newer. This is from Microsoft Research Asia. Definitely worth checking out. And this brings us to the next sort of generation I want to talk about. And this is NERF. So NERF stands for Neural Radiance Fields. These are a thing that came about, we're looking at under 2 years ago. And actually the funny thing was, I'll tell you sort of a funny story is, maybe some of you know Andre Karpathy is the author of, is the director of AI at Tesla. And I was on a call with a paper reading call with him one time, probably about a bit over 2 years ago. And the interesting thing was he made a joke that, nowadays, everywhere I go, I just take my phone and I just take pictures of everything. Like, he said, because one day I feel that like we'll be able to turn it into 3D or something. And literally within, a couple of months of him sort of saying that, NERF was out. And did exactly what he was sort of describing. So you can see here that we're basically, what is NERF, right? We're taking a bunch of input images, and we're generating so we're taking a bunch of these input images, and we're sort of generating a scene that we can sample not just from where the original images were taken, but from anywhere around that scene. So we're actually rendering whole new views here. So the idea here is that we're using a neural network to learn a scene from sparse inputs. The other thing here is that we're actually doing what most people would think you don't want to do with a deep learning model, is that actually we're overfitting on the scene. So it's not like one model can learn hundreds of different scenes, right? You tend to use one model for one scene. Certainly, where these things started was that. And what we do is we overfit the network to learn a scene, in these weights. And it turns out that this is a much more efficient way of storing this information than trying to make some sort of 3D model or something like that. When they started out, this would take like 30 minutes to 60 minutes to generate, something really small, like one of these. So it wasn't super efficient at the start, right? It has speeded up probably by about 2 orders of magnitude, since then. But this is some examples, from this. So I can see someone's asking some questions. Is NERF the same as photogrammetry for 3D models? Okay, I don't know exactly what that is for 3D models. It's not really making a 3D model in the traditional sense of like a Blender or something like that is a 3D model. What it actually is doing, let me see, do I have any pictures? No, I don't have any pictures. Okay, so imagine that, let's say we wanted to do my hand, right? Imagine that at each point, if I take a picture from over here, there's going to be a certain amount of light reflection from there. And we're training the neural network to be able to predict sort of the density and the amount of light reflection at that point, and actually for every other point along a array. And then we're doing that for all the different rays. And so it turns out that when we've got a picture coming from this side and getting the ray there, and we've got one going from this side, these are going to be roughly the same. And so it can learn to then basically reproduce views that it hasn't seen images for. And you can see that's what's going on here. So they, the idea here is that we're basically sort of sampling, multiple views, but from this overfitted model. So let me just sort of, I'll give you some code to play with for this. I've just run this through tonight. So here's an example of an image, right? And you'll see that at the start, when we run this kind of thing through, it's going to be really bad. That it's not going to, at early on, it's going to, and it's doing it for all the images that it's got for this. I'm just sampling it from one view, right? But it's actually generating from all the different views. And you can see at the start, it's just a blob, right? It's not even a very good blob. And then, but over time, given enough iterations, it starts to get that, oh, there are different colors in different parts. And there are different, things that are going on in each of these parts here. And then given enough sort of, enough training, it can then start to get a lot more accurate at being able to do this. And each time that it's going through, it's basically predicting each point, sort of doing like a ray tracing kind of thing there. It's not a traditional sort of ray tracing thing, because we're actually predicting at every point along the ray. So even the bits that are empty space, the model is kind of learning that, oh, that's not going to reflect anything because it's just empty space. And so you can see that just taking something like this, okay, here we haven't trained it. This is not trained for too long at all. This is just a tiny sort of version. But if we take that and we then basically render something out, we can then move some of these, and we can then actually render out a video. So you can see that that's definitely getting the 3D sense of it. Now, obviously, this is a much smaller version than the model in the paper, but it gives you an idea of like what's actually going on with this kind of thing. Let me just go back to the presentation. So NERF is so I see a number of people are very interested in this. I don't know a lot about some of the 3D modeling stuff you're asking me about, so I can't really compare it exactly to that. I do know that this is the idea here, is that this is definitely a much more efficient way of doing some of these things. And it's also, it also allows you to do some really cool stuff. So this paper, I think, was a little bit about about 2 years ago, something like that, the original NERF paper. And then Google followed up later that year with this paper called NERF in the Wild. So NERF in the Wild is pretty cool, right? This is the Trevi Fountain in Rome. If you, I'm guessing quite a few people know that. And what we're actually looking at is a lot of pictures that were taken, but they were taken from Google Photos. So you could imagine that Google Photos has thousands and maybe, tens of thousands of photos of Trevi Fountain where tourists went there and took pictures at different times of the day. And you would have even seen people standing in front of it, etc. And you can see that what this model is able to learn in this case is not only the scene from different viewpoints, but the scene from different lighting, lighting over the day and stuff as well. So this is something that's really kind of cool how it's done it. Now, what would have happened if there were people in front of it? If there was a person in front of it, obstructing there, they would have only been in one picture. So the model would have learned that, okay, yeah, for that one picture, there was a reflection, there was a light point that would have bounced back at that point. But given thousands or tens of thousands of images, it's able then to sort of filter the people out. So they have a really nice example of this one, and they also have a nice example of the Brandenburg Gate. If you go and have a look at, NERF in the Wild, that's one really cool. So this idea is now making its way into other things as well. So at NRIPS, we saw this being used for animation. So we can do things like where we can use some sort of open pose model to do poses, and then we can generate the sort of NERF from that, and then basically translate this into 3D. And talking to the StyleGAN guys, one of the things that, like I said, a lot of this talk came out of just chatting with these guys for an hour or so. One of the things that they were clearly interested in, and one of the things that they hinted at, but obviously couldn't say straight out, is that they see the future as being sort of like GANs for NERF. And we've had DeepMind kind of do something like that with at a very small scale. But I suspect that you will see, this team is going to release a paper probably in the next month or two. There's going to be some sort of generative GAN take on a NERF idea. And so this is sort of like a precursor to this. Sure enough, after NRIPS, NVIDIA released this. So NVIDIA is StyleGAN, for those of you who don't know. And they released this. So this is basically they called the instant NGP, or instant neural graphics primitives. And what this is doing the same idea as a NERF, but it now allows you much more freedom to move right throughout the different the different scene here. So I've downsampled these just to put them as GIF files in my presentation. If you look at the original one, especially this particular one, it is amazing, right? You're looking at a 3D, a totally 3D world. It's very high resolution. I encourage you to go along and have a look at this link and check it out. The other thing that I sort of hinted at before, but so we originally were at like 60 minutes to make, 30 to 60 minutes to do a model for a tiny little object. Then we got it down to sort of like 3 to 6 minutes, and then it got down to sort of like 60 seconds on one of the papers. With this paper, it's down to 6 seconds for training the model that can do the whole thing of this. So clearly, NVIDIA is very bullish on this kind of generative model, in that what they're sort of seeing is my guess is that they can see that this is going to be used heavily in games, heavily in the metaverse, all these sorts of, fancy, cool stuff that's coming. A lot of it will start using some of these things. And you could imagine that you've got one model that represents this whole street scene, and that model could be pretty tiny and put into a game. And that would allow you to fly around. Now, don't forget, we're looking at a particular path that, is going, but you could have gone any path in there. Right, it didn't have to be this path. That it's not rendered just for one path. It's rendered for any path that you would take through this. So NERF ideas, very cool version of generative ideas. How am I going for time? Conscious of time. Okay, the last one that I want to go through tonight is another very cool idea, which is starting to take off, and people are starting to talk about it. And this is the idea of diffusion models. So what is a diffusion model? So these things have lots of different names. This is one of the sort of downsides of some of this stuff is like GANs was pretty cool in that everyone just, oh yeah, GAN. Diffusion models, often called denoise and diffusion probabilistic models, also called sometimes scoring models. They have, each of the papers tends to have a slight different take on it. And I would say we're almost at the point of working out some of the best ways to do it. Maybe not quite there yet, but pretty close to this. So if you think about a GAN, I'm just going to bounce back and forth with this. If you think about a GAN, right, we've got our latent noise. We take that latent noise, we feed it into, some sort of upsampling model. And that's how we go from this sort of, this 512 dimensional vector up to an image. So the diffusion idea is very different from this. Diffusion idea is much more like an autoencoder. So if you think back to, I'm guessing most of you who've done any sort of deep learning at some point have either seen or used built an autoencoder, right? And the idea is that you're predicting the same thing that whatever you're putting in, you're predicting the same thing out, usually. And you've got some sort of bottleneck where you're getting it smaller in the middle. So you've got this encoder on one side, decoder on the other side. And they were one of the first things that deep learning sort of took off, and people were kind of amazed, and people kind of threw them away because they weren't that useful. They were useful for denoising certain things. They're actually quite good in certain time series models and certain things where you need to deal with outliers in data and stuff like that. They can be really useful. But this idea of diffusion models has brought this all back. And it's kind of brought it back with a vengeance. So what this does is it basically says, right, we're going to start off with a nice image. And each step, we're going to basically add just the slightest amount of noise from, say, a Gaussian distribution. So we've got a nice Gaussian distribution. We're going to add a slight amount of additive noise. And we're going to normalize after each step as well. And then gradually, we're going to go from this image to something that is completely just noise. Right? Now, inside that noise, it turns out, though, that there are some patterns, maybe not patterns that we can see, but there are patterns that a neural network can then learn to do the reverse of this, where it can take the noise in, and over many iterations, and I'm talking about a lot of iterations for some of these things, often they will be sort of at the high scale around 4,000 different steps, and at the low scale, maybe 25. For the particular paper I'm going to show you, low scale was 25, the high scale I think was 4,000 or 8,000. But at each step, it basically predicts the next image that would be slightly less noise. And you can see that we've got this noise thing there, and we've got slightly less noise. And then gradually we get back to our picture of a dog. Now, like I said, here we're doing it in 11 steps. In the real model, you're doing it probably, for thousands of steps. But the cool thing is your model then learns to be able to take all different kinds of noise and translate that noise into something that becomes out the other side, which is a really, a sort of photorealistic image in this case. And you could imagine that we can guide this noise just like we can do with the things that we saw. All the guided generation tricks that I talked about before, they can apply to any of these kind of models. So we can then sort of use this, as a way to take a loss against some sort of text or something else, as we go through this. So the idea, let me just go back and make sure I've covered all this. So the idea is that where these diffusion models learn by breaking an image with noise and then rebuilding it from that noise. And the model learns to create the image over many, many iterations. What it actually does is that you end up with a model that you can then pass in a certain amount of noise and a certain time step to then predict the next time step. So I can sort of say, right, this is the noise after 387, iterations. Give me the 388th iteration from this, and the model will then be able to translate it as it goes through. So one of the papers at NRIPS this past year was again the same authors from DALI and from Jukebox, from the OpenAI guys. And these two seem to do a lot of things together. And what they basically said was, well, what if we just do the diffusion idea on ImageNet? And so they basically did exactly this, and it turned out that it actually is better than a GAN. This style actually beats GANs at generating things on ImageNet. So ImageNet GANs, especially any of them that have used some sort of ImageNet model, you'll find that they often mess up the eyes really badly. There are a lot of artifacts and stuff like this. Here you can see we've got a diversity of classes from ImageNet. I presume everyone knows what ImageNet is. If someone doesn't, feel free to ask, but I'm guessing that most of you do. We've got a really good sort of diversity of things going on here. And I just realized I ran some code before without checking it too. So we're going to get a surprise in a sec. All right, so we've got this. We can then compare this to other models. So the sort of closest model to this previously before that Style XL GAN, the one that's just come out, in the past couple of weeks or so, would have been Big GAN from DeepMind. And if we sort of zoom in and look at this, we can see that Big GAN really messes up the faces, right? So this is the class of a particular type of fish. And we can see that this is getting fish, and we've got variety in generation, but we've got some really weird characters here. Whereas when we look at the diffusion model, it tends to produce things that are much more realistic. And then we look at the real world data, we can see that, okay, this is actually from the training data. So you can see that, sure enough, the diffusion model is producing a better set of quality images here than the GAN way of doing this. And they have a number of different ways for doing this. There's some really nice tricks in there of what they'll do is they'll use labels to classify the normal and noisy versions so that you can then condition on a class that, okay, I want to take this noise and I want to generate the fish image, or I want to generate the panda image. And the model is then able to work out, okay, now if I've got this kind of noise and I've got this class for panda, I need to create this kind of image of a panda. And that's what allows us to get nice, variation of what's going on in there. And it can what it actually does is it shifts the noise too. So it works out that, well, this bit kind of is panda-ish over here. So I'm going to push that up and expand that, and that's going to become my panda from this. So this is a paper from NRIPS, a very cool paper that sort of introduced the idea of these diffusion models for actually really big sorts of things. Taking it a step further, the same authors, and you can see they sort of take it in turns to who's going to be first author for this. They released a model, or they released a paper called Glide. And what Glide is, if we think back to DALI, one of the models I talked about before, DALI was using that VQ idea in the generation. What Glide is, and then was using Clip for guiding it with a text prompt. What Glide is doing is exactly the same, except instead of the VQ idea, we've got the diffusion idea. So this is very similar to the DALI paper, except it uses diffusion, uses the exact same data set. Turns out that this is much less, this is less blurry than what we've had before, and it can be guided with Clip. So you can see that with this, you can actually then highlight areas and with a mask and sort of say, right, I want to change it, from just an empty field to, zebras roaming in the field. And sure enough, it's able to generate things like that. I want to put a white hat on a guy, and it can do that, quite easily. Let's actually have a look at let's have a look at some code for this. Okay. So I ran this literally as we were setting up, and we had a bunch of issues with the link. So I forgot to come back and look at this. So this is a clip demo this is a glide demo of where we're using clip to generate it. And so it's basically doing the diffusion stuff. We can set the amount of diffusion steps that we want to do, etc., and go through this. And we're using some pre-trained clip models that we can use for an image encoder and a text encoder. And then we basically put in a text prompt. So the text prompt that I put in and literally just ran it and forgot about it was an oil painting of the Sydney Harbour Bridge. So I had no idea whether this is going to work or not. So I'm basically telling it to generate a batch of 8 images of the Sydney Harbour Bridge. I've got some different things to do with how much do we want to listen to the clip guidance or not that we can sort of set in here. And you can see, sure enough, it will generate images that are 64 by 64 pixels. These look pretty good for the Sydney Harbour Bridge, right? And then we can upsample these to be 256 by 256. And we can see, sure enough, this is turned out. And so I think I said, as an oil painting. Yeah, an oil painting of Sydney Harbour Bridge. And you can see that definitely some of these look like an oil painting. Let's just try it. I think I can do this. What if we say something like a watercolor? I'm guessing they're going to use the US spelling, so I will put that in. Harbour Bridge, I've got. Okay, let me just see how that's going to go. So this is, hang on. Okay, I need to run it all again. Let's let it run. Maybe I'll come back to it. Anyway, I'll come back to this at the end. Okay, so Glide is definitely, one of the sort of most recent models. And this is, again, we're using this, what I want you to sort of see and hopefully take away from tonight is that it's still using the same sort of guided generation patterns. And that these things end up becoming sort of components of where you just slot different things in and out. And that wasn't the case, a couple of years ago, right? Each of these things now is starting to mature so that we kind of know, like, okay, if I want something where I'm going to have a text prompt involved, I probably want to use some sort of clip model in there. And I'm going to use some sort of text guided generation with the clip kind of thing going on. So this is something that we can sort of look at. If we look at some of the conclusions, there are many tools for generation now. There are ones that I haven't covered tonight, but I've tried to cover the main ones that I think are the most interesting. The other one that I didn't get a chance to talk about is normalizing flows is also a really interesting thing, but it seems to have gone slightly a little bit out of fashion. The diffusion stuff is definitely the hottest stuff at the moment. To give you a sort of idea of this, one of the guys that I know from DeepMind tweeted out about a week or two ago, about GANs, something about GANs. And I casually asked him, so what do you think about diffusion models now? And I got an answer back like, oh, yes, these things are really cool. And then sure enough, he put out a blog post all about it. And pointing out some of the cool things that why are these things cool? They are getting much more, sharper images. When we compare something like DALL-E to the Glide, you'll find that DALL-E tends to be more sort of cartoon images, that kind of thing, whereas Glide will be much more in the sort of sharp image, that kind of thing. How's this going? So this is loading up a model. Okay, I'll come back to it. So you're going to see that the other thing I would say is a key takeaway is that you're going to see these key components that keep popping up, right? And I'll go through some of those components in a moment. And if you sort of get your head around those components, you will see them again and again and again. And when you go to read papers of this stuff, you'll sort of get a sense like, oh yeah, okay, they're doing the clip trick, they're doing this trick. And you can sort of work out, oh, okay, this is the new cool thing about this paper, and sort of hone in on that. There are still areas that vary a lot. The VQ thing is really cool in some ways. And it's definitely, it's definitely got a place, but the diffusion models is also cool in a different way, and it's certainly starting to take the lead now. And then we've still got GANs, which are really useful tools for generating images, etc. So just some of the components you should be aware of. We've got encoder decoder, right? So that's a common thing you're going to see in all these kind of models, whether we've got, a vector quantized encoder decoder, where you can even think of the diffusion thing as an encoder decoder in the way that it's doing it. We've got the vector quantization and code books idea is popping up a lot. We've got the idea of doing things in steps. So the diffusion models and also the flow models, which I didn't get a chance to talk about tonight, also do things in steps and deal with, they're dealing with distributions of data in steps. You've got the adversarial component, which is still a very strong thing that we see in GANs, etc. We're also starting to see, transformers make their way into these things. So all the things for the text. Now, generally what people are doing is encoding the sequences of text with a transformer model. And they're also doing the same thing for images as well, that you can sort of pass a transformer, pass an image into a VIT, a vision transformer, and get some really nice results out of those sorts of things. So that sort of, gives, these are some of the key components we're seeing again and again. Variations, there's definitely a bunch of different variations that people are still trying things out. The whole idea of distribution comparison. So one of the ways that's become very popular is KL divergence, but people are trying out different ideas. Another thing is taking different losses at different parts of the network. So like I showed you in the projected GAN, where you're taking, you're basically taking a loss at different parts in the network for that, but also in other models too, they're taking multiple losses and adding them together, maybe balancing them, etc. You're seeing the whole idea of sort of likelihood-based models versus implicit generative models is something that's coming along too. What you should look out for is that, mashups. You're going to see a lot of cool stuff, I think, this year in the idea of mashups, is that people are now starting to realize, oh, we could take the VQ idea from here and the GAN idea from there. So, and that actually has happened. There's a really good model called VQ GAN, which uses some of the vector quantization ideas with the GAN. You've seen diffusion and stuff like this start to come about. Like I said, I do think we're going to see over the next few months some really interesting stuff with GANs and NERF, and maybe even sort of diffusion ideas in NERF as well. All right, so let me just check back on how's our still loading. These models can be pretty big. That's the one of the downsides with working with this stuff is that training it is usually going to be out of the realm of most people. Sort of training from scratch. You can certainly do a lot of fine tuning of these models and get some good results there. Anyway, in this is the slides. If you want to get the whole slides for tonight, and I've got links for the two notebooks, etc., and some stuff more. There's a nice post about VQ, VAEs if you're interested in that kind of thing. Another thing is if you're interested in this kind of thing, so we also run a meetup. We're in the same time zone, which is kind of amazing, right? That's very cool. We run a meetup called Machine Learning Singapore. Myself and my co-founder in the company started this in 2017. We have like 4,600 members or something. We run events at least usually every month. And we used to run them at Google. Obviously in COVID now we've moved online. So we sort of do a lot of stuff that's sort of cutting edge stuff like this, but we also do, more sort of general stuff. One of the things that we actually do is we teach some courses and stuff with, for the Singapore government, and we've trained people from Google, from Facebook, and this kind of thing. So, if you're interested in sort of going to more meetups, right? If you want to come on, I don't know what we're going to do for the next. I think for the next coming meetup, I'm probably going to talk about some new stuff with ConvNets that's out. But we generally have the two of us give a talk. And then we sometimes have guest speakers and stuff as well for this. Questions. If you want to reach me, you can email me or contact me on Twitter. But if people have got questions, I'm happy to go through. Let's have a look at how's our Sydney Harbour Bridge watercolor. Now that's turned out pretty nice, right? Let's look at those. So you can see here, it's really got a sense of watercolors. That for me is very nice. And you can see also here the sort of composition of a watercolor is actually quite different than an oil painting, right? It's quite common, I guess, in watercolors to have, just blank white parts. So we can see sort of that there. We've got some really nice colors going on there. Maybe we try watercolor of the Sydney Harbour Bridge. Fireworks. Let's see how that goes. All right. So this is the glide model. It will generate at 64 by 64, and then we'll basically just use a simple super res model to upsample it for this. Okay, questions. Okay, what is Sam working on at the moment? Okay, so I think my co-founder is going to speak to you guys in a couple of weeks. He might show you a demo of one of the things we're working on. We're working on, oh, look, there's with the fireworks. That's not bad. Not great, but not bad. All right. That one definitely is fireworks. So we're working on, what are the things we're working on? A lot of different things. So we do a bunch of stuff, like the big thing we're really bullish on at the moment is virtual people. So imagine instead of talking to a chat bot that you're actually speaking to something that looks just like a real person, can read your face as well as your voice, and then you can basically have a conversation with it. This is something that we've been working on for the past couple of years. We've had some papers at different conferences around sort of parts of this, and we're now sort of hoping to release this as a product later this year. So we're actually looking for sort of customer, sort of trial customers for some of the things to do with that. The other things that we're working on is we do some work for the Singapore government. That we can't really talk about that much, but some of that, is really interesting. We're also doing a bunch of training for the Singapore government as well. So basically, working with them, Singapore is very bullish on the whole AI thing. And so we've worked with a number of people in various, parts of the government that are data scientists and training them up to sort of be AI engineers and deep learning engineers. So that's sort of one of the key things. Other questions?
There's a question about, is nerve the same as photo?
Okay, so I don't really know what the photo. I've lost that question. I'm just trying to scroll up and see it. So you're also asking about structure from motion. I don't really know what structure from motion is. That sounds like it's something that's probably quite specific. The key idea with the nerve thing is that you're kind of doing like a ray tracing idea, like you do in in a game or something, but you're fitting it into a neural network, and it, and you're kind of breaking some of the rules, because we all get taught, oh, don't overfit models. The the thing that, is that you're overfitting the weights, but it turns out the weights is just a much more efficient way of storing this. And we're literally just at the beginning of all of this. So like I showed you that, instant GP model, I think that came out in January, yeah. And from what I've heard from people inside NVIDIA, chatting to some of these people, there's a lot of more cool stuff that's coming, that they're trying to sort of work at, that they're working on. I know from Google, so we have a lot to do with Google. I know that Google's working on similar sorts of things. You do find that OpenAI, if you know a little bit about the sort of ecosystem, OpenAI tends to do things that are very controversial, or to attract a lot of attention, like GPT-3 and stuff. But Google and DeepMind and NVIDIA and Microsoft will often have just as good technology, if not better, but they're very hesitant to make the big claims that like OpenAI is making. So there's a lot of really interesting things that are going on like that. I think actually Martin is going to talk to you in a couple of weeks. We'll talk about DeepMind's retro model and the Google Lambda model, which are two language models that are very interesting, things that are going on there. But anyway, yeah, in regards to NERF, it's definitely something you want to sort of check it out. And literally, it seems with every paper, the rendering times are just getting, faster and faster and faster too. For this. Okay, what is ImageNet? So someone's asking about ImageNet. Great, okay. ImageNet is originally a competition that was in the early 2010s. And someone's posted a link, that's great. So ImageNet is an interesting data set. It was actually a data set, right? And a competition that was made. And it actually was made by some people who became quite famous later on. One of the authors on that paper is a guy by the name of Richard Socha, who went on to be the head of AI at Salesforce. Lovely guy. Some of you may have even seen him. He taught at Stanford for the NLP courses in Stanford for a while. He's now gone and started off his own startup. He's doing a whole bunch of really interesting stuff as well. But ImageNet itself, what made ImageNet sort of so key was that you had this idea of like you've got a million images, you've got 1,000 classes, and for the first time ever, people were able to predict build models that could get very high levels of accuracy. And when we say very high levels of accuracy at the start, they were sort of around 76, for top one accuracy, they were probably in the 50s to 60% accuracy. Top 5 was around 70 plus. And then gradually each year it just got better and better and better. And it's also where the first place where deep learning had its sort of major breakthrough, in that the previous scores that people were getting before deep learning, the error rate dropped by 50% when deep learning was introduced. This is also the first place that things like GPUs were used for this stuff, and techniques like dropout. A number of sort of key techniques popped up in these ImageNet models. And so in 2012, you had this model called the AlexNet model. In 2013, you had Clarify, which basically had a winning model that beat Google. So the AlexNet model was by Hinton, if you know who Geoffrey Hinton is. That led to him and his students selling a company for $40 million to Google. There's a whole bunch of interesting things around that. But each year the models got better and better. After sort of 2017, 2018, eventually they abandoned the competition. They abandoned the competition for a few reasons. One was because they'd already surpassed what the human level was. So I mentioned Andre Karpathy before, who is the head of AI at Tesla now. Andre used to be at that stage was a PhD student at Stanford. And so he decided, wouldn't it be great for us to know what is the human accuracy on ImageNet? And it turns out that ImageNet is actually quite tricky, because even though you've got 1,000 classes, there's about 120 classes that are just dog breeds. So unless you know a lot about dogs, I look at it and I'm like, yeah, that's a dog, that's a dog, that's a dog, right? But so what he did was he sort of taught himself the dog breeds and then did it. And he tried to get a bunch of people in the Stanford AI lab to do this with him. But after people sitting there for like an hour of doing it, they were just like, yeah, forget it, I'm not going to do it. And so he worked out from himself, the human level being the Andre Karpathy level was about 5% error rate for a human. And that's on top 5. DeepNet surpassed that, deep learning surpassed that a while ago. So it got to the point where they decided to abandon the competition, but it's still a benchmark that is used for everything, and that data set is used for everything. So a lot of the GANs will train up on that data set to show how well they do on a standard data set. But yeah, it's a good question for asking about that. Can you share more about the near future trend of NERF and the metaverse? So I think that you will see the metaverse is marketing technology, is sort of marketing term. You will definitely see a lot of interesting things coming for, some stuff like that. We're also very interested in NERF for rendering different things. So you'll probably see some big tech companies release glasses maybe late this year, early next year, that allow people to do, the whole augmented reality thing. And you will then be able to use things like NERF and some other models to render things right in front of people in 3D. And there's a whole bunch of technologies around that, but some of these things like NERF are actually starting to get that to be really good. You mentioned earlier, not many industry use case yet, so particular barriers. Okay, so that was more about the GANs, in that the GANs originally didn't have a lot of use cases in the wild, because they required a lot of data to train. They were quite hard to train them and stuff like that. You can actually use them for data augmentation. There are certainly some tricks that you can do for that kind of thing. We're seeing now with like the GALGAN, version 2, that's clearly going to get a lot of use in industry, in that people can take a pre-trained model. And you could imagine you could have a pre-trained model, for example, on furniture that's just trained on 1 million images of furniture. And then you could say, right, I want to design a piece of furniture and I want it to, I want it to have this shape, and I draw that and I tell it, but I want it to feel like, fur or something, and it will render, all that sort of stuff. So you'll see a lot more things like that. Previously, GANs were used a lot for the things like style GAN were for facial recognition models. It's very hard to get facial recognition models. And then for certain organizations, generally the data sets and the models for facial recognition either tend to fall into being Western or Chinese, meaning that the model was trained on Western faces and is very good at Western faces, not so good at Asian faces or any sort of indigenous face, something like that. And then you've got the Chinese models, fantastic on Chinese faces, not so good on other faces. So one of the things that that we saw that worked quite well for fine-tuning these models was to go into a style GAN and generate up the different ethnicities that we wanted, and that kind of thing. So that's something that you can do. But there weren't a lot of uses for that, is what I was sort of saying. Have you started working on AI in metaverse? If you have, can you share a bit? And so definitely what we're working on could be considered as part of the metaverse. We don't really think that much about the metaverse per se. What we're interested in, if you know the TV show Westworld, we're big fans of Westworld. And we think the only thing that Westworld got wrong is that it won't be, it probably won't be in person for a long time to come. It will be virtual. So it will be in AR and VR. So that whole thing of sort of rendering, realistic people is one of the things that that we're doing. Maybe I can find a demo. Let me just quickly look for something. So that's something that we're definitely interested in, and that's something that we've sort of seen that, like, okay, we're on the verge of a lot of things coming through. SE ImageNet has been around for 10-15 years. So the original ImageNet paper was in 2009. Yeah, okay, so yes, someone's answered the ImageNet question. Yes. Originally, it was based on a data set of words too that went with it, but that never really took off. What are the next upcoming conferences where work on generative models will be presented? So there are a number of different conferences that are coming up. We've got ICLR coming up in about 6 weeks, 8 weeks time. We've got the CVPR, which are all the visual conferences. There's a number of those sorts of things coming up. So you will certainly see new stuff, and you'll find that the companies have to release their papers. So normally you submit a paper sort of 4 to 6 months before the actual conference. So some of the things I've shown you tonight will be in conferences over the next few months. And then things that get released, over the next month or two will be, probably over the next 3 months would be things for NRIPS at the end of this year. So the conferences themselves trail a little bit behind that kind of thing. Thoughts on most promising applications 5 years out? Okay, 5 years out. That's like, so I guess the only thing I can think about is going 5 years back. 5 years back would have been, 5 years back, 2017. At that stage, GANs were just starting to take off, and everyone was really bullish on these things, and they've definitely gone sort of beyond even what I thought they would get to. One of the biggest things that we've seen in the past 5 years is also AutoML, or the idea of neural architecture search. So using a deep learning network to build another deep learning network. This is still hugely successful for a lot of things, and Google's doing a lot of things with that as products and stuff like that to basically make it easier for people, etc. 5 years out from now, definitely everything will be multimodal. So you'll see that, like, we've gone mostly for images or text or things like that. In the future, we'll have everything. I think you'll find that even things like audio, visual, text, all will start to be combined in models. And not just for generative models, but for sort of classification models, that kind of stuff. I think we will see some really interesting advances. We will definitely see, deep learning make a huge impact on health. DeepMind is already working on that a lot, and has really done some amazing stuff with things like AlphaFold, AlphaFold 2, that kind of thing. I don't know if we're going to see, reinforcement learning pay off more. That's something that, reinforcement learning can do amazing things, but then it's still like, maybe it hasn't delivered on what people have promised a lot for it as well. But we will see, definitely a lot of interesting stuff over 5 years. How do we extend techniques into 3D? My understanding of NERF is that it's not general. So meaning that it's not a generalizable model. Like, we don't use the one model to train for lots of scenes. We tend to use one model to render a specific scene. Yes. So the idea of rendering dynamic scenes, this is a really interesting idea. And this is something that DeepMind has worked on with just small objects, of where, you can render objects that actually don't exist in the real world, and then build sort of like a NERF model around something that doesn't exist. That I think you're going to see a lot more of this year. That's something we'll definitely see a lot more of this year. And any thoughts of ML development in Asia versus Oceania? So I really don't, know what's going on in Australia at all. I have, some friends there and stuff like that, but I don't, there's definitely a lot of talented researchers there. I know that Google's starting to invest more, to do, I think Google Brain is opening up there. So that I'm not sure about. Generally, for most things in deep learning now, it's becoming China versus, America. That is definitely true. And you're seeing, a lot of the really cool stuff starting to come out of China, often more than it is coming out of America. That is something, I think one of the things is they just have a different view about data. Also, the ethics around data and stuff like that is quite different. I know Google flew me up to China in end of 2018, something like that, and talking to a lot of the local guys there, I was amazed at how far they've come along and and I'm not talking about sort of like top class researchers. I'm talking about young kids, like just talking to kids who've just come out of university and stuff. And they're really doing amazing things. So in sort of Southeast Asia, I think probably similar to Australia, you're seeing, people are starting to realize that this stuff can be really useful and can be, can certainly make products and stuff like that a lot better. One of the courses that we teach is deep learning for product managers. And we've seen a lot of people be very interested in that, of sort of learning not the technical stuff as much, like we teach a little bit about building models, but for that one, it's more aimed at product managers who want to know what's possible, what's not possible, and then how can they, what they would need in data, what they would, learning how to sort of build an AI product is a very different kind of product than what most people kind of, see for that kind of thing. That's something that we sort of see is popular in both in Asia, but also in the West as well. Diffusion model sounds cool. Wonder whether it's been applied to non-image training data. Yes. So yeah, I didn't get a chance to talk about it, but diffusion models are also making their way into speech systems. So we do a lot of stuff around TTS, or text to speech. And some really nice, just, past couple of weeks, there's been some nice papers from Tencent in China come out using diffusion models for TTS systems. So that you're definitely going to see that more. And it wouldn't surprise me that you see something like, the jukebox using diffusion from OpenAI soon as well. I think that's it. If there's more questions, I'm happy to answer them. But
it's really cool. Is there any more questions? We can have one more question, one more last question. Yeah, please open your mic if you want to ask question. But it's been a really good, yes, any questions?
Maybe I can ask people a question. I'm curious, I was asking the organizers just sort of, who are the people on the call and what do you guys do? So I'm curious to sort of know, like, what sort of ML are people working on, or deep learning? Do you do it in your day-to-day job? What sort of are you all working on recommender systems? Are you working on, what do you guys do? If people want to just type something in, it's just. I see everyone's getting really quiet now. Yeah, and exactly. Feel free to open your mic. Yeah, I guess that's one of the cool things about being on the Meet system. Computer vision for pathology. Okay, that's definitely something where deep learning is being used a lot. Chip design. Okay, so we've trained some people from Infineon, and I know, and yeah, chip design is definitely something also that Google's very interested in. And you're actually saying it, so I don't know, Sean, whether you probably know it already, but Google released a really big paper about using reinforcement learning for chip design recently. 3D structure from motion for shipwrecks, but not using ML and DL. See, now that's really interesting. Like that's something that maybe you could use the nerf thing eventually for some things like that. You know, that might be something that you could do. All right, it's cool. Yeah, it's cool just to hear what people are doing. I'm always interested to sort of know, okay, what people are working on, what things that they're interested in using deep learning for. Martin and myself, my co-founder, we've trained probably a few thousand people in deep learning now around the world. I did a stint in New York. We've trained for Google. We've trained in the West Coast and stuff as well. And we sort of see that like it's really cool when someone's got some domain knowledge and then learn sort of the deep learning skills to go with that, and then apply that and get amazing results. So that's something that's really cool. Now for the near future, wants decent initial point clouds. Cool. Okay, applying NLP to investigate job trends. Okay. NLP is something that we've worked on a lot for people. That's definitely the area that's probably one of the hottest sort of key things now, that just wasn't working as well 4 or 5 years ago, and suddenly now with transformers is working amazingly well. All right. Anyway, thank you. I think I'm certainly happy to answer questions. If people want to email me or anything like that, like I said, if you are interested to go to more meetups, feel free to join our meetup. We do events there. But it's cool just to sort of meet people from different places.
Yeah, well, thanks a lot, Sam. It's been really interesting, like a talk this evening, and then I've been receiving a lot of good feedback from people through the what is it, the survey. Some of them like have already filled out. If you haven't filled out, please do fill out. Yeah, as Sam said before, we actually are going to have another meetup with Martin. Martin is like Sam's co-founder for Red Dragon AI. And yeah, it will be, we are looking forward to, and we're gonna inform you later in regard to the meetup. And then the other thing is like, I would just want to thank you for Xian and Sarada for the collaboration and for co-hosting this event. And yeah, it's been really great to work with you guys, and hopefully we can work more in other meetups. And there are different kinds of options that we have now. And you guys specifically in the machine learning, yes. And then Sam also has a event in Singapore as well. So it's a free world, and everyone can learn more every day. And at GDG, as for all of you here, like we hosting a lot of different kinds of technology meetup, and also a lot of different types of Google events. And then we are looking for collaboration with different kinds of communities as well. Well, before we go, can I ask everyone to maybe perhaps like whoever left here, if we can take a picture together? Is it possible?
And let me just say thanks for having me. Thank you.
Well, thank you so much for you having coming today, and it's been a bit late, right? Like,
Yes,
okay.
Sam, I just want to say, like, thanks for your huge enthusiasm. You know, that was a really great run through the kind of whole field of GANs, which is great. And your energy throughout that was absolutely awesome, and you stayed on point right the way through, which was brilliant. So, thank you again. That was a great talk. And yeah, Dr. Sarah, thank you for putting that together. We really appreciate you bringing in the resources to do that. So yeah, thanks again, guys.
Everyone. Thank you so much, Sam. And yeah, so let's take picture together. Whoever here. Okay, let's do it. 1, 2, 3. Okay. Thanks a lot, Sam. I'm looking forward to talk more with Martin. And thank you, everyone. Oh, okay. Let's take another picture. All right. Yeah, it's good to have another girl here. Okay. Well, thank you, everyone. Have a good night and stay safe and healthy. Bye.
Thank you, Sam. Thank you, Eunice.
Bye, everyone.
Have a great night.